Hey, my name is Jonas Kulhanek and I'd like to present you our work titled WildGaussians, where we extend 3D GS to in the wild captures. Recently we've seen 3D GS dominating 3D reconstruction, and it achieves great quality with real-time rendering speed, and it allows for greater editability and control over the reconstructed scenes. It works really great when we have high quality input images captured under ideal conditions. Unfortunately, this is rarely the case, and in real-world captures we often get occlusions when people move in front of the camera, and when this happens you get a reconstruction which looks like the one shown in the video. Another issue is when you want to reconstruct the scene from data captured by various users, captured at different time of day, a different season, and under different illumination conditions, and all of these images have very different appearance, and this is something that 3D GS couldn't handle because it does not explicitly represent the appearance. And what 3D GS tries to do in this case, it tries to put semi-transparent Gaussians in front of the cameras to change the overall color of the image. For example, for night images, it would place semi-transparent black Gaussian in front of the camera to make it look darker. Is there something we can do with this? This is what we try to achieve in our recent work. So first of all, we added image embeddings to each training image, and then we also added Gaussian embeddings to all the Gaussians. Then we added a tiny MLP which takes as the input the Gaussian embedding and the trainable embedding, and it outputs an affine color transformation. And we use this affine color transformation to transform the original view-dependent colors stored in each Gaussian. And this gives us, for the original set of Gaussians, this gives us a new set of colors. And so we use these new Gaussians and apply standard 3D GS rendering pipelines to get the final rendering. Now let's talk about the uncertainty. So in order to learn with uncertainty, we take the ground truth image during training, and we take the DINO features, and we apply an uncertainty predictor on top of the DINO features, and this gives us an uncertainty map. And then we compute a normal loss function between the render output and the ground truth image, and we weight the loss function by the predicted uncertainty map. So how do we optimize this uncertainty prediction? So we again take the DINO features of the rendering, and we also take the DINO features of the ground truth image, and we just take the cosine similarity between the DINO features of the ground truth and the rendering, and use this for the target for the uncertainty predictor. So let's take a look at some results. Here we show the results on the NeRF on the Go dataset, and on the left you saw NeRF on the Go method. You saw the 3D GS method on this data, and on the right you see WildGaussians, and you see how WildGaussian removes all these floaters while keeping the rest intact. Next we show the comparison with a popular NeRF-based method. So we pick K-planes, and as you see, the NeRF-based method first of all has less detail, also has some floaters, and when we compare to 3D GS, of course 3D GS cannot represent the different appearances, so like you only see the mean appearance, but you cannot represent the night scene or like scene with slightly different colors. So thank you very much for your attention, and see you at the poster session on Wednesday in the afternoon.